this first? No, why not? All right. Let's keep our life simple and look at the picture on the left where I have a pipe that might skinny down to a smaller diameter. Wrong direction. Sorry. Something like that. A1. Are they using 1 on the left? Or is it 2? 2. 2. That's fine. All right, so imagine this thing's full of water. I have flow going from left to right. You guys okay with that idea? Does it seem reasonable that fluid would accelerate toward a region of lower pressure? Why?
Because pressure likes to balance.
Pressure likes to balance. How big's the force over here? If I have P2 over here, if there's pressure on this end of the pipe, P2, how can I calculate the force at that point? P times A, I agree with you, A2, yes? Wouldn't that be the force over here? Yes. And there's a force here on this end, sort of resisting, if you will, the flow of water going the other direction. So realize if I apply a force here, I've got to move this slug of water on the end some distance through the pipe. And if I apply a force through a distance, what am I doing? Work. Okay. And at the same time, I've got other forces doing negative work, because they're resisting, if you will, the application of the force on one end of the liquid by pushing against the direction of motion. What kind of work would that be? First of all, what kind of work is this? If I apply a force here, and I get this liquid moving to the right in the same direction, what kind of work? Positive, thank you. Good. And then if I have other liquids resisting that force, pushing in the other direction, while the water is moving that way, what do I call that kind of work? Negative, yay, negative work. So if I can do work on this system of water by applying a force on one end, while I know there's resistive forces on the other end, I'm doing work on the system. And when I do work on the system, any kind of work on any kind of system, what do I get? A change in. If I do any kind of work on any kind of system, what does that lead to over here? One very important energy idea. A change in what? In what kind of?
Mechanical energy?
Almost. Kinetic energy.
Oh.
What's that theorem called, guys?
Work
Work energy theorem. Okay. If I do any kind of work on any kind of system, it will lead, well, the net, if it's network not equal to 0, it will lead to a change in kinetic energy. Now, if you guys remember, going back in the Wayback Machine, that work can be due to non-conservative forces or conservative forces. What kinds of things are conservative forces in our lives? springs, but in this case, looking at the picture on the right,
Pressure.
gravity, yes? Gravity's a conservative force, and if you recall that conservative forces are equal to minus the change in potential energy, you remember that? I can move that conservative force over here, and I get this. This is looking like total mechanical energy, right? Okay. So in this case, in our water pipe instance, we are applying force to the system, an external force to the system that is not conservative. In other words, something's pushing on one end of my system of water. And it's going to lead to a change in the mechanical energy of the system, either in the kinetic energy, or if I get a difference in height of the water, it's going to lead to a change in the potential energy, or average potential energy of the water. Boring. Okay. This should look somewhat familiar to you, I hope. Maybe. You know. Okay. So, the work here is this guy. It's force through a distance. Realize I've got pressure 2 times area minus there's some resistive force doing negative work on this little slug of water. Okay, so I've got this force pushing this way, this force resisting, doing negative work, and the difference between those two is the net work. But this is not work, this is force, so I need to multiply by some distance factor, correct? So I'll call it some distance d through which that work is done. I get 1/2 mv2 squared plus 1/2 mgy2. Oh, not 1/2. Goodness. mgy2. I'm going to add my total mechanical energies here. Did they do that? Oh, they did 1 minus 2. 2 minus 1. Odd. Oh well. Minus. What's the big idea? I'm doing work on the system by applying forces on one end. I have resistive forces opposing that. Force through a distance is work. It will lead to a change in mechanical energy of the system. Okay. Now, if I think about A times D, what is that in general? Area times length. Volume, okay? So if I divide both sides of this thing by the volume of the water that I'm thinking about, it will disappear over here. And what is mass over volume? Density. So I get 1/2 rho v2 squared rho g y2. drop? I dropped it. But the bottom line is the following. If you manipulate this, had I written it correctly, you would end up with this. And this is the important equation to take away. You don't have to know the derivation per se. That is definitely correct right there. And I'll explain what it means. So make sure that boxed equation is in your notes and we'll explain what these pieces mean.
Your ones and twos are off. That's
Ah. Well, in this equation they're not.
And
I
the
know
bottom
this,
one,
I
not
dropped a
one.
minus sign somewhere in here.
It's your twos and ones. You got them mixed up.
They're just
But they're still.
in opposite places, they're still.
No, it's okay. No, they're all twos here and they're all ones over here.
Yeah, your bottom one, but the one above it.
Oh, is that what happened?
Yeah.
Oh, help me.
So that would be
Help.
that would be a V1.
Where? Here?
Yep, that would be V1.
Why?
Because when you move your P1 over.
Oh yeah, I've dropped a minus sign somewhere in here. I know this is not gonna work well. But don't look here, just know that the work we do on the system leads to a change in kinetic energy and potentially the height of the liquid. Got it? Okay, and in manipulating all of that, you should come up with this equation. I'm gonna talk about this equation, okay? This is important. I've screwed this up somewhere. I apologize. Let me turn off this and let's talk about this equation in detail because it's super important.